Okay, so where we left off the last video was just finding this last answer for number 6 from the homework, or the suggested questions, and I was writing it down as the video ran out. So it's 3.71056 to the negative 19, and that's a joule down there, just in case you can't tell. Okay, so that was the final answer. All right, so like we spent quite a few videos now on photoelectric effect. So why? Why is it so important? Well, remember, it was one of the 2 key experiments that forced physicists to take another look at what light really was. And because of it, we had to say, well, you know what? Maybe light is a particle. And then came to the theory of the dual nature of light, that not only is light a wave, it's also a particle, and depending on the circumstances, it will act sometimes like a wave and sometimes like a particle. So it acts like a wave when it's interacting with other light. So when it's interacting with other light sources, then light acts like a wave. But when light is interacting with matter, then it acts like a particle. So that's one of the reasons why the photoelectric effect experiment is so important. The other reason is because it opened up a whole avenue where we could invent things using it. We use the photoelectric effect a ton of times in our lives. You use it without even knowing it. So you have to think, so there's a photosensitive metal, and it's connected by an incomplete circuit to another side. And what completes the circuit is us shining light on this photosensitive metal. Because then when we do that, electrons come across and the circuit gets completed. Now you might say, so where the heck do I use this in my life? But if you think about things in our lives where if something is blocking the light that's being shone on a photosensitive surface, then whatever this circuit is hooked to doesn't work. One of those examples could be a TV remote control. So the TV remote control is sending infrared light onto a photosensitive surface on your television. Now, I mean, maybe digitally we've changed this, but it's certainly how it always used to work, and I didn't Google it to make sure that it's still all remote controls are like this. But if you stand in the way or put a sheet of paper in the way of that remote control, then the light, or if you're not lined up correctly, the light doesn't hit the photosensitive metal, the circuit isn't completed, and the TV doesn't turn on. Elevator doors. If you've ever noticed they're about to close and then you put your foot in, you put your body in, and they stop opening. When you put your foot or your body in, you are blocking infrared light that is going from one side of the elevator door to the other to a photosensitive surface. When that light doesn't reach there, then the circuit is incomplete and the elevator door is programmed to not close. Think about if you've ever robbed a museum, and hopefully the answer is no, you haven't. And here I am teaching you how to do this. No, not really. All right, so in a museum, they use lasers in their security system, crisscrossing like all over the museum. If you've ever watched a movie like Pink Panther or anything where they're trying to break in and they're stepping over the laser beam and under the laser beam, or actually the Big Bang Theory does the same thing when they're playing a game. So this laser beam is being shot at the other wall, and on the other wall is a photosensitive surface. And when the laser beam strikes it, electrons are released and completes the circuit, and all is well. And so your security system is programmed so that if anything were to cut this laser beam, so that now there's no longer light shining on this surface and no longer electrons flowing through the circuit, then an alarm sounds. Okay? The scanners in a grocery store are photoelectric effect. The speed zones, where it tells you as you drive up, like in a school zone, and it flashes like the speed you're going when you're only supposed to be going 30 or something, and it flashes. They're using a photoelectric effect. Even the street lights use photoelectric effect. So just for fun, if you're bored and have some time on your hands, sometime between now and whenever this lockdown is done, you might want to Google present-day uses of photoelectric effect. You will be shocked at how many uses there are. Okay? So that's really the other reason why we spend a fair bit of time examining it, because it will come up in your life more than once. All right, I had said some time ago there were 2 experiments that caused us to relook at light. The other one is called the Compton Effect. Sir Arthur Compton did an experiment where he took high energy photons. Now remember, photons are little packets of energy. Okay, so they have no mass. They're kind of like Ziploc bags filled with energy. So they're little packets, little particles, but they move as a wave. So Arthur Compton took a high energy photon, high energy short wavelength photon, and shot it at a surface. And when he did that, he saw that an electron was emitted. And you have to stop and think about this. Remember, the law of conservation of momentum says that momentum can neither be created nor destroyed. So initially, this electron is sitting here on this surface, and then after the light hits it, the electron gets thrown off. The electron now has some momentum. And if the electron has some momentum, it must have gained it from the collision with the light, from the packet of energy. And as Compton examined it, he saw that also given off was a lower energy photon. So going in was a high energy photon, and then coming out was this low energy photon. And I purposely made the wavelengths, right? Short wavelength means big frequency, and big frequency means high energy. So this is a high energy photon, and this is a low energy photon. But maybe what should have caused you to pause would have been, but wait, how can the electron gain momentum from a photon when in grade 11 physics we learned that the momentum of momentum of an object is mass times velocity, and a photon doesn't have a mass, right? We know that any particle moving at the speed of light cannot have a mass. But photons are light, so therefore they're moving at the speed of light, so they can't have a mass. So how do they have an energy? Okay, so photons do not have masses. That's not part of what happened here. But what happened here was we had to come up with an equation for the momentum of a photon. And so we define the momentum of a photon to be its energy divided by the speed of light. Okay, we define. That means we didn't discover it, we defined it. Okay, so now the energy of a photon is HF. So it's HF over C. But remember, C equals F lambda. So then this is really HF over F lambda, and the F's will cancel. And so the equation we usually use for the momentum of a photon is just H over lambda. From this equation, we can see that the units for momentum are kilogram meters per second, just in case you don't remember them. If we do the units down here, Planck's constant is joule seconds, and wavelength is meters. But we know from work is equal to F delta D cos theta that a joule is a Newton meter. So we have a Newton meter second over a meter. The meters cancel. So we have a Newton second. And remember from F equals MA that a Newton is a kilogram meter per second squared. So we have a kilogram meter per second squared times a second. The seconds cancel. We get kilogram meters per second, which is the unit for momentum. So it does work. So this is the unit, this is the equation to find the momentum of a photon, not dependent on mass. Suggested questions for tonight, page 571, number